Hi everyone, welcome to today's guest speaker session. Here today we have Colin. He's a first year PhD student in computer science at UC Berkeley, advised by Professor Joseph E. Gonzalez and Professor Trevor Darrell and Professor Anne Stoica. His research focuses on multimodal interactive intelligence, including visual agents, robotics, and volumetric and temporal generation and understanding. He's a civil scholar in computer science, and his prior work has been adopted by several frontier vision language models, including OpenAI, GPT series, Google Gemini, and QuenVL. Yeah, glad to have you here, Colin, and over to you.
Hi, everyone. Thanks for coming and thanks for inviting me and organizing the session. My name is Zirui. I go by Colin. Again, I'm a first-year PhD student at UC Berkeley. I work on multimodal models, and I have a focus in pushing the frontiers of multimodal interactive intelligence. And today, I'm excited to present our recent work, VisGym, diverse, customizable, and scalable environments for multimodal agents. This is joint work with collaborators from Sky Computing Lab and Berkeley AI Research, all from UC Berkeley. So before we dive into this research, I wanted to start with a crash course on agent to provide broader context. So, one sentence summary, AI agents interact with the environment to solve problems or tasks for humans, right? So for example, if you want to book a flight, clean a room, or even play video games and just want someone to farm the monsters with your account, you might want to use an agent to complete the task, right? These agents in AI, in the AI era, they can broadly be a large language model, can be a humanoid or some other kinds of robots or multimodal large language model, right? Such as a vision language model. You let them interact with the environments related to your tasks. For example, a browser with HTML representation, a room with cleaning tools, and the game with observations, inventories, and monsters. And once they complete the task, they get back to you, so you don't have to do these by yourself. So these busy are agents and their duties. And now one particular case this research based on is multimodal agents, right? So in one sentence summary, these are agents that perceive more than text from the human and or the environment side, right? So for example, human can set up a task specification to the model, like for example, what the room should look like after cleaning, how a physical tool should work in video after being fixed, etc. Right? You pass these information to the agent, which is usually a multimodal model like GPT, Gemini, Cloud, Grok, and they deal with the environment to complete the task. So these are multimodal agents. Now, given the basis of multimodal agents, I think the domain itself unlocks a lot of useful applications. Many real-world problems are multimodal. For example, you have web agents that do everything on the internet. You have robots that resolve physical problems. You have agents that can refine graphic interface design or more broadly front-end and more, right? And whenever we have an emergent domain, we need three things, okay? So first, we need evaluations. We need evaluations that are indicative of their capabilities. And there are existing evaluations like OS World that examines computer using agent, Liberal that benchmarks robotics. Second, you need training data, right? We need data to train the models to become good multimodal agents. For example, you have MMAT for computer use. You have Colin for robotics. And third, and I think it's something that people often ignore, it's a playground to understand the limitations of models and data so we can develop better recipes. We want something that can evaluate agents in a diverse range of domains, extremely customizable so that you can isolate and study almost every design choice in your agentic workflow, and extremely scalable so you can use it as a data generator to figure out what training leads to at scale, right? And this is VisGym, which we title it Diverse, Customizable, Scalable Environments for Multimodal Agents. So on the left, you see our 17 environments spanning spatial reasoning, manipulation, puzzles, navigation, and perception. These differ in a lot of attributes such as observability, dynamics, and visual structure. And the key point is that these are visually grounded, interactive, multi-step tasks, not single-shot QA purely in text or in vision language, right? And on the right, we show a rule-out example of the 3D maze environment. There are some basic properties. For example, this is a partially observable environment. The agents needs to actively explore to know how the layout of the maze. And it has a 3D structure where you cannot really treat it in the text space by representing 3D in text. And whenever model sees an observation, it generates an action in terms of what to do and how to do it, right? So for example, if it wants to move forward, which is represented by a word move, followed by number 0, right, which means forward. And we provide a list of everything it can do and the way each action can be done in the text instruction from the initial prompt. And we have a demo here. So for example, the model at the beginning, it sees the instruction, right? So what are the available, what is the goal of the task? What are the available actions? And for each action, what is the action space? Like how the model can do within that action space, right? So it sees this instruction and then it interacts with the environment. Basically, by providing the action, it receives the environment feedback with this kind of visual feedback, right? So like it generates a new observation, also with some text feedback, and makes a further move, to actively explore the environment and gradually to solve the task, right? So this it keeps moving forward, and then once it hits a corner, it learns to take a turn, right, and to kind of explore until it hits the goal, which is this kind of red dot here, right? And we have like 17 environments of them. I will give a snapshot of each of these 17 tasks because understanding them is pretty important in understanding like the takeaways from all of these tasks. So we have 17 tasks. The first task is colorization. In this task, you basically are matching a color as precisely as possible. So on the left, you see a color wheel that shows the current hue and saturation. On the right, you see a circle filled with the color placed over the target area. The border of the circle marks exactly where the original color comes from, and the goal is basically to adjust the hue by rotating around the color wheel, adjust the saturation by moving in and out from the center until the color matches the original color at the center of the circle. And when the model is satisfied, the basically call stop to submit the answer. This is counting, right? You need to count how many objects, in this example, number of horses, appear in the image, and to help the model track, they can place a dot in each horse they see and mark them one by one, right? If they make a mistake, they can undo their last mark. And once they're confident that they marked every horse, they could just submit a final answer as a total count. And so this is this task. Pick and place, this is one of the Mojoko tasks using robotics, right? So basically the agent controls the robotic arm to pick up a gray cube and place it in the target location. They see two views, a front view of the robot and a camera view attached to the gripper. They have to use kind of discrete moves, right? Like so move to like -1, 0, 0. That's toward a certain axis. Like X, I think it's X axis -1. Hit the gripper left or right, forward, backward, up and down, right? So basically move the gripper to align with the cube, then close the gripper, grabs it, and next carry the cube to the right target marker and position it correctly, right? So this is this task. Rich, similarly, you also have this kind of robotic task, but it's a simpler version than pick and place that you only need to kind of reach the red object instead of like having to move it to a target position. Jigsaw, this is a pretty common visual puzzle that children also play around by a lot. So in this task, model are solving an n by n, in this example, 3 by 3 jigsaw puzzle where all the pieces are scrambled. The goal is to kind of rearrange the pieces until the original image is correctly reconstructed. So the model can either swap two pieces by selecting their grid positions or reorder all the pieces at once by specifying their correct order from top left to bottom right. Matchstick equation is where you have a broken matchstick equation made of digit and operator symbols, and each step you can move exactly one matchstick. Take it from a specific segment of one symbol and place it onto a specific segment of a different symbol, and until the left-hand side equals to the right-hand side. Matchstick rotation, this is one of the special tasks where the model needs to align the blue stick with the right target stick by translating and rotating it. So the tricky part is that the action units are not calibrated, right? So the model doesn't know. So if I say move -23, it is actually not reflected. Like we don't have access. The model needs to kind of explore the relationship between visual changes in the text action to understand how the dynamics work, right? So each step, the model chooses how far to move in X and Y and how much rotating degrees, and then observe the result and adjust. And the goal is basically to iteratively refine the position and angle until the blue stick is within a small tolerance of the target, and then stop to submit. Mental rotation 2D, this is a simple one. You basically have like two views of like one target and one reference, and the model kind of needs to rotate the target, the right image to the reference image in terms of same angle by calling the rotate and by observing the visual feedback. Mental rotation 3D is kind of more complicated because this time it has like partial observations, right? So it's still the same as mental rotation 2D, except that this time it is a 3D object represented in a 2D space, right? So the model needs to learn how the object looks like before determining, well, what is the correct rotation that would rotate this object to the other to the reference position. And then the cube is like a synthetic renderings where we render synthetic cubes, and this where we take from like a set of real world 3D object called objectverse. So this is a data set. Partial assembly, this one you're kind of resembling an M by M. In this example, 8 by 8 grid using X, right? And in this example, 6 irregular pieces. So the pieces start parked around the board, right? And your goal is to kind of place them inside the grid so that the entire grid is filled with no gaps and no overlaps. And the model calls place a certain index like 3 and into like 0, 0. So this is what the model does at this step. Referring dot pointing, this is like you're kind of selecting a specific object in an image, right? So the prompt basically provides you need to kind of select a specific image, and the model needs to find and the model basically needs to find the x, y, and coordinates between 0 and 1, and then point to that object. Of course, the model can change the point if it figures out that its current selection is off the object. Sliding block is that you basically have like a sliding block puzzle on an M by M, in this example 5 by 4 board. So the left panel shows that target configuration, like you need to kind of shuffle the pieces into this specific configuration. The right panel shows the current arrangement that the model needs to transform, and each move the model basically selects a block and slide it one step up, right, or down or left, right, as long as the space allows. And the goal is to rearrange the block so the current board exactly matches the target layout. Mid-2D, this is simple enough, right? So you basically need to move to the target within a specific step budget. Video on shuffle is that you have to kind of reconstruct the timeline of a short video. So the model needs to call swap and reorder to kind of like swap or reorder the pieces so that like if you read the sequence from left to right, that's basically reconstruct the keyframes of the video in the correct order. We also provide like a short description of the video as the initial instruction to help the model understand what is happening. Zooming is like you have like different image crops by zoom level. So the model needs to kind of order these patches from least zooming to most zooming in this kind of reference image. And here is an interaction thumbnail of basically all the environment we have. So we have like 17 environment, and each environment has its own data, its own characteristics, its own task specifications, and a set of like capabilities that it tests on those kind of multimodal agents. So now back to the abstract level, we have 17 tasks in total. Some taking observations based on real world images, 3D objects or videos. Some are based on synthetic renderings, and in terms of observability, some tasks are fully observable, meaning that the model knows everything about the environment layout without exploring, and some require exploration to know the layout of the environment, right? We also have environments where the model needs to explore to understand how its actions change the state or observations of the environment, which we classify as kind of known and unknown dynamics. And each environment has a set of actions, and each action has a specific action space, basically available actions and the parameters. Any questions so far on the environment design? If there's no questions, I can move on to the first and most exciting analysis part. All right, cool. So now, moving from the motivation and an extensive overview of what VisGym is, I wanted to kind of go down to some concrete stuff and review the basics of an agentic workflow. So from a very high level perspective, an agentic workflow is where human specifies the task instructions to a model, right? So the model serves as an agent to interact with the environment to complete the task. And in this workflow, there are multiple factors that can critically affect how the same agent performs. For example, how much history we want to keep in the interaction context between the model and the environment. What modality, right? So what modality do we represent the environment? What feedback do we need from the environment? And how we should set up specifications or for goals, right? And with VisGym, we were able to experiment with all of them for visual agents, and I'll talk about them one by one. So first, the first key design question is, how much history should we keep for an agent, right? And so in general, there are three options, right? So no history, partial history, and full history. And on the left, we highlight tasks that involve learned dynamics, like ridge and matchstick rotation, where the agent needs to understand how its actions changes the visual state. And on the right, we highlight tasks that involve learned feedback, like sliding block, maze navigation, where the agent needs to interpret feedback signals over the time. So intuitively, both of them seem to require some notion of memory, but it is not obvious how much history is necessary. And here's the result. So you see, we basically evaluate 4 frontier models. 2 are closed source, GPT-5, Gemini-3-Pro, Pro, and 2 are open source, Quinn3VL 235B Instruct and GLM 4.5V. For all of the experiment, we keep the same 4 models for consistency, and the left plot is the average, right 4 plot are like performance on specific tasks, right? So x-axis shows how much history we keep from only the current turn, which is like basically 1, to the full trajectory, which is the infinity label, right? And the y-axis is the average success rate. So we see a very consistent pattern across tasks and models. So adding some recent history helps a lot, but because the model can see its recent actions and the visual effects, right? But keeping the full history does not keep helping. So in many tasks, performance saturates, and in some tasks, it even drops. The performance even drops. So the takeaway is that model needs context to reason about its action-effect relationships, but you should not assume that more context is always better, because this could be something related to its training distribution or whatever. That if you just provide all the history, in the better case, it causes a performance saturation, and in the worst case, it causes a performance degradation. Another key design question is, do we represent visual observations directly as images, or do we convert them into text? So here we show several environments like matchstick equation, sliding block, maze, and patch reassembly. And for each, we have the default visual rendering, and we also have like a variant where the same state is represented in text, right? So if you represent it in text, you don't really need a vision language model. You can simply use a large language model to solve the task. And the motivation here is that text representations can make structure more explicit, right? And reduce the perceptual burden that is placed on the visual encoder. But they may also lose spatial or geometric information that can induce maybe helpful, helpful prior, basically. And the pattern is clear from the results. So when the environment is visually structured and discrete, right? So like grid and block layouts, text representations help a lot. So models perform better when the structure is kind of explicit in text, like maze 2D, patch reassembly, and sliding block. But there is one task, matchstick equation, that shows a different trend, right? So if when the task relies on visual priors or fine visual patterns, like those kind of like Figlet style fonts, image input is still important. Text loses those kind of critical visual cues. So the takeaway is text can bridge a gap between perception and reasoning for structured tasks or for structured representations. If you have like a representation that is more like a grid or like a matrix, I think text sometimes benefit a lot more than vision. But visuals are still necessary if you have like specific geometry or appearance patterns. Another design question we study is, do agents need explicit text feedback from the environment, right? So in many of these tasks, especially those that require fine-grained vision, models frequently make illegal or invalid moves. For example, like you move a matchstick that does not exist. You do a sliding block into an unoccupied space, or walking into a wall in a maze, right? So these are all illegal moves. The environment can either just stay silent and just update the visual state, which humans can probably be satisfied with that, because if humans try to make a move and see that it doesn't change the visual state, then they realize that something's wrong, right? Models probably do not, right? So we additionally provide text feedback like, this is an invalid move, or you cannot move there. So the question is, does adding text feedback help agents learn and correct their behavior, or can they purely rely on rely on visual signals like humans mostly do, right? So across all these all the same models and all the aforementioned tasks, the pattern is consistent on this question. So when text feedback is available in addition to visual feedback, right, performance is significantly higher. And when we remove the text feedback and only keep the visual feedback, basically the new observation, the performance drops sharply. So the takeaway is simple. Current models are not good at inferring state transitions purely from vision. They rely heavily on those kind of explicit text feedback signals to correct their behaviors and to guide their behavior. And finally, which I personally think is the most interesting design question and that we study is, do we explicitly tell the agent what the final goal state should look like? So here you see tasks like patch reassembly, zoom-in puzzle, jigsaw, matchstick equation, and colorization, right? So in all of these, it is easy to define the operations, but it's hard to imagine the final target state from the initial observation, right? So if you only look at the initial observation of patch reassembly, where all the patches are parked around the grid, I think it's very hard to construct a mental model like what the final goal should look like, right? And so the question is, if we provide the final goal explicitly as part of the instruction, should the model perform better? I think intuitively no one's gonna say no, right? So for humans, if you provide those, so the final observation should look like this, should look like that. Humans should probably do a lot better than if you just ask them to just complete the task without like giving them how the final observation should look like, right? So intuitively, I think no one's gonna say no that if you provide a final observation, the model is gonna perform worse on it. But I will show you that this is actually the case. So for tasks like patch reassembly, jigsaw, and colorization, giving the goal helps significantly. And in contrast, for zoom-in puzzle and matchstick equation, performance actually degrades when we provide the final goal. When we analyze their failure modes, we found that models often judge that the initial goal and the final goal observations look exactly the same when they're actually not. So they just stop at the beginning and they stop immediately calling, oh, the initial observation looks exactly as the final goal observation, so we just stop. So the issue is actually not just about a lack of long horizon planning or imagination. It is also a failure in fine-grained visual discrimination and change detection. So the takeaway is goal visibility helps when imagination is the bottleneck, but this can also backfire when this kind of precise visual comparison or perception capability is lack of for models. So moving on to the next part, I want to show you like what insights we found by fine-tuning models to be good agents for our environments. And I will decompose them into 3 perspectives. So generalization, different modules contribution, and data curation strategies. Let me briefly explain our supervised fine-tuning setup. So we use a heuristic-based multi-step solver to automatically generate expert demonstrations for each environment. These give us full action trajectories, not just final answers. We study in 2 settings. So we have like single task fine-tuning where we train on one environment at a time, and mixed task fine-tuning where we basically train jointly across all the environments. And all the experiments are done with Quinn 2.5 instruct 7B using full parameter fine-tuning. We use about like 100K demonstrations for single task fine-tuning and 350K demonstrations for mixed task training. So now we ask a very concrete question: is supervised fine-tuning alone, without doing RL, sufficient for difficulty generalization, right? So if you train your model with supervised fine-tuning on an easy level of the maze task, so if your maze is always 7x7, and during inference you present a maze that is like 11x11 or even harder, can the model solve it just with SFT fine-tuning without like RL, right? So we focus on tasks where increasing the difficulty leads to substantial state changes, not just small parameter tweaks. So for example, jigsaw, matchstick rotation, maze 2D, maze 3D, patch reassembly, video on shuffle, and zoom-in puzzle. So you see that in all these tasks, you change the difficulty, you change the dynamics or the layout of the environment significantly. Basically, for example, number of pieces in jigsaw, number of moves required in matchstick equation, the maze size, the patch and board size, and the number of pieces you kind of have to reorder for video unshuffled and zooming auto. So this is a clean test of whether model actually learns transferable structure in their multi-step problem solving capabilities, or they just memorize the easy setting. So one sentence summary is basically we train on easy and we test on both easy and hard and see how it generalizes to the hard difficulty. So here's the takeaway. On the left, you see the average success rate when we train only on the easy difficulty and evaluate on the awesome and hard variants. You see that performance drops, right? So like from 0.59 to 0.14, and for the other model, there is a drop from like 0.64 to 0.32, right? This is expected, but it is far from zero. And more interestingly, Quinn 3 generally is better than Quinn 2.5 across all the tasks. And the takeaway from this single plot means that a stronger base model usually benefits more from the same supervision. And here's the second. So now in this plot, each point is a task, right? X-axis is the performance on easy, and Y-axis is performance on hard. And that diagonal would mean perfect generalization. So what we see here is that some tasks do not generalize through SFT alone. Like, for example, you see those kind of like jigsaw or matchstick equation. You train on easy, the performance could be like 0.90% success. But if you evaluate on a hard on this hard version, the performance is basically zero, right? However, you see that there are some tasks that really benefits from there are some tasks that generalizes really well. Just with supervised fine-tuning on the easy data, like for example, this kind of maze tasks, right, and zoom-in puzzle for some of the models. So the key insights here is that generalization really happens at task level. So if a task that shows generalization on model A is likely showing generalization on model B, and vice versa. So this is less a model thing; it's more specifically a task-specific setting that causes a generalization. Another question we ask is what actually drives multimodal multi-turn capability, right? So our hypothesis is that there are two key factors. So first, we need a visual encoder that is strong enough to capture those kind of very small visual changes across turns. So basically the state transitions caused by actions. And second, we need a strong LLM, right? So the LLM needs to be able to temporally ground its decisions because the LLM sees all the past histories in terms of like the visual changes, but the visual encoder only sees the visuals one at a time. So that means that the LLM needs to do the heavy lifting to integrate and reason over past observations and past actions, and not just the current frame. And to disentangle these two, we have a setting where we train in a mixed task setting, and then we do a clean ablation. So in one variant, we freeze the visual encoder, so only the LLM learns. And in the other variant, we freeze the LLM, so only the vision side learns. So this lets us isolate whether gains are coming from better perception or better temporal reasoning. And here we plot LLM gain on the x-axis and vision gain on the y-axis. So each point shows which module contributes more when we fine-tune. The first takeaway is that most tasks are in the upper right? So that means that they benefit from fine-tuning both the visual encoder and the LLM. So that means that there's a synergy. Like if you fine-tune both the vision encoder and the LLM, this is where most of the gain happens. And then there's a clear pattern. So you see some of the tasks with partial observability, which we mark them in like blue circles, right? So tasks with partial observability and longer dynamics, like maze 3D mental rotation, they lean more towards LLM gain, which are represented as this kind of like the points below the diagonal line. So this means that history integration is the bottleneck for this type of task. And you also have like a range of tasks like patch reassembly, zoom-in puzzle, colorization. You can imagine these tasks really require those kind of fine-grained visual structure, right? And they lean more towards the vision gain, which are represented as points above the diagonal line, right? And that means the perception is a bottleneck. So if you only have to fine-tune one module, that is probably the vision encoder. So which module matters more is also task dependent, but in a general sense is whether the task involves more fine-grained vision, which means that you should probably fine-tune the vision encoder if there's only one part you can fine-tune, or the LLM if you matter partial observability and longer dynamics, and then you need a stronger LLM to kind of integrate the history. And the final training question is driven by the characteristics of the visual environments. So many VisGym tasks have partial observability and hidden dynamics like mental rotation 3D, right, and matchstick rotation, right? And even though the rules are given, the model never sees the full state or the exact transformation, right? It has to infer the changes from visual differences or comparisons across turns. And a natural approach to kind of supervise with is to supervise with full solution trajectories. But that mainly teaches the model to replay the steps. What we really want is for the model to learn how its actions changes the environment, so it can leverage its existing context to make better decisions, right? So longer context, better decisions. So this has forced us to think carefully about like whether we're training to learn those kind of imitation, or are we actually training the model to understand the dynamics and to make better decisions based on its exploration and its context. So on the top, in the unknown dynamic setting, training on 3-move solutions perform much worse than decomposing into 1 unit move plus solving moves. So that means that if I have like a supervision signal where in the first step I always teach the model to make like a very small move just to learn how the unit changes the visual states, right? And then model basically can leverage this kind of existing information in its context to make better or more grounded, accurate moves in later, right? So this shows it is learning how actions changes the visual state, just not just memorizing the actions. And you see this basically improves the average success rate by 2 times, right? By curating better data. And on the bottom, and in this partially observable case, right, we see the same pattern. Solve-only supervision is kind of weak. If you teach the model to kind of rotate the object along all the axes and then you solve this task, it works much better. And you see the rotate then solve strategy in terms of training data curation improves the inference accuracy by 2 times as well, right? And this is not really caused by if you have a longer trajectory, it naturally improves the model or having more geometric exposure in training. This is not the case, right? So if you teach the model the right behavior with more data, and then you teach the model, and then from this checkpoint, you continue training the model with the solve-only data, it actually causes a performance degrade, right? So that means that the takeaway is that when dynamics are hidden, solution-only supervision is kind of brittle. Data curation should expose transitions and exploration. If you have to curate SFT data for multimodal agents, they help model learn better and perform better at inference time. And in the end, I wanted to finalize my talk with this question. So how do frontier models perform on VisGym? So we tested models like GPT-5 and Gemini-3-Pro on all of these tasks in the easy and hard settings. And we show that for these apparently easy puzzles, frontier models can only succeed in less than 30% of episodes in the easy setting and less than 15% in the hard setting. And people often overestimate how multimodal agents actually perform. So if your visual agents cannot even perform well on these kind of fundamental visual puzzles, would you trust them to be deployed in your production workflow, right? But the good news is that the models are improving, and I think, yes, this is evidenced by our current internal evaluation on the latest Gemini-3 models and so on. And you should keep an eye on our website because I think we have already updated that. And I believe like 2026 will be the year where we see a significant improvement in multimodal agents that are not doing so well right now. And that's all I wanted to share. Thanks for listening, and I'm happy to take any questions.
I think we have one question. Rabius.
Yeah. So what's the reason for which phenomena? Sorry, I missed the message.
Yeah, no, Rabius, if you can just explain the question a bit.
Which which phenomena? I also okay.
Okay. And anyone else has any more questions? I have a couple of questions.
Yeah, okay.
Yeah, but I just want others to ask if they have any. If not, I'll just ask. Okay. Okay, yeah. I just ask. Like my
Yeah.
question is more on the broader side of like what made you choose only like these categories? Like, did you do uh, like has in the talk you did mention that like what are the VisGym, right? In
Yes.
those like it kind of the frontier models right now are not performing really good. Like, did you just go about creating the tasks which are what hard to perform in terms of like right now the state of the models, or it's just like what's
I,
the reason behind just creating these things?
okay. I think multimodal agents, there are kind of like, I think the most trendy applications of multimodal agents nowadays is like probably people heard of is one is computer using agent, right? So
Yeah.
you, and the second application is robotics. Also, like they kind of like separate the robotics in terms of like visual agents, but I mean, like
Yeah.
robotics are doing exactly the same thing as multimodal agents because basically they need to ground its past actions or observations to make accurate and grounded actions in the future, right?
Yeah.
So the reason that we choose these tasks, uh, there are two reasons. I think first, these tasks highly mimic the scenarios that web agents encounter, right? So in web agents, the agent has access to a computer, right, to a website,
Mm.
but it does
Yeah.
not know, like, if it clicks a new link, what will happen? Maybe the link is broken, or maybe it clicks in the wrong place, right? So
Yeah.
it basically shares a lot of like similar patterns that we have in this task. Like, do you need text feedback, right? So if you click in a blank space instead of the actual link, and
Mm.
realizing that the frame didn't change, right? Well, the model gets stuck, or it needs to get some text feedback whether the link is actually successfully clicked or not in order to proceed.
Yeah.
But we choose this task because we don't want to kind of let models do tasks that are kind of overfit, because we know that a lot of agents that are already trained on a lot of like website episodes, right? So
Mm.
we might be good web agents, but that's basically only a pattern of overfitting to a specific domain. So we really wanted to test something that shares some of the similar patterns that the agents encounter in general, but are less contaminated in the training data. So we can expose the fundamental limitations of multimodal agents as if they were saying something that is completely new, but sharing the same patterns and dynamics that it encounters in scenarios that are familiar with. So that's why we pick this range of tasks. And I think also these tasks, a lot of these tasks involves like those kind of continuous transition, where
Mm.
you make a change, the visual transition is kind of continuous, right? You can't really turn them into text, like those kind of pick and place and rich. And I think those are also indicative of robotics performance. So we think the fundamental reason that we choose this task is that they span in a diverse range of domains, and at
Mm.
the same time, they solving them requires capabilities that are shared with some of the most common multimodal agent applications, like web using agents, or sorry,
Mm.
computer using agent and robotics. And that these are less contaminated, so we can directly measure their capability uh, in a less overfitted way. So
Okay, yeah, got it. Makes sense. So, like, do you think like these days, like whenever someone releases like these kind of benchmarks or something, so they'll quickly kind of models will get like better performance, like even like in 6 months or 1 year, something like that. Like do you have any like estimation on okay, like maybe by this year or like maybe by next year, the models will get really good at these things, and if it is so, like what's stopping them right now in terms of getting really good performance, like other than you did mention that even the what are the tasks you have taken are kind of more unique kind of. That's what I heard. So
Yeah,
did I?
I I got what you're trying to I think like basically you're asking like why the models are not so good on this
Yeah,
task, how people should kind of improve their models.
yeah,
um I think these tasks seem hard for multimodal agents because I think most of the multimodal agents are overfit to specific domains, and they don't
yeah,
work out of the box for a different set of tasks that shares the same capability, but are just different in domains, right? So
yeah.
I think if we I think there is one slide. Let me find that slide. So there is one slide. How do frontier models perform on VisGym? We actually show that there is a specific model. So you see this UI TARS 1.57b. So I think this is a ByteDance multimodal agents that are specialized into in UI interactions, right?
Okay.
This model, I think it gets a lot of traffic on open router, right? So a lot of people use it for them to kind of use the agent to
Mm.
do those kind of UI navigation tasks. But you see that this model actually can only solve like 1.5%, basically 1.6%
Yeah,
of spatial puzzles in the hard setting. So that means that even though models seem to have like those kind of multimodal agent capabilities in a specific domain, those capabilities don't really transfer. It really overfits to a specific domain. So that's why when we're testing those same models on different tasks that require the same a similar set of capabilities, it failed massively. So I think those kind of transferability of capabilities is really something that people should work on in order to kind of improve multimodal agents in general. And I think
yeah,
the way that we kind of want to make sure that the capability transfer is to use reinforcement learning, because using reinforcement learning, you don't mess up with models pre-trained distribution. Like I think the pre-trained model has seen a lot of like scenarios that it generalizes, but you really need a good training objective to correctly elicit all the capabilities without destroying the model's representations, right? So if you do
mm,
SFT, yes, model learns all the skills, but at the same time, if you have like a limited domain, basically you see there is a representation collapse, right? So model only
mm.
knows how to model only know how to solve the task that is within a specific domain with a set of capabilities that are required. But if you move to a different domain, it just fail because
Yeah,
Zirui already kind of like breaks up the model's internal representation of a diverse, a diverse word, like everything that it sees in pre-training. So I think we really kind of need better RL infrastructure, our
yeah,
algorithm to do those kind of multimodal agent training, so that model learns the capability by sampling from its own distribution without basically breaking its general representation of the world.
okay, yeah, makes sense. And like one more question is that uh, like I see maybe you mentioned it, maybe I missed it, is that like all these models that you have tested is it
Yeah.
like just normal models, or you also tested the reasoning models in terms of like Gemini 2.4 Pro thinking? And like because we have seen like in a lot of benchmarks, when you have like normal model and thinking model, the thinking models will perform a bit better than the normal model. Like did you even go through that lens on how the thinking aspect of it is performing in these scenarios?
I think this is also a good question. Like basically comparing the thinking model and non-thinking model. I think we have some of the things. I think we turn on the thinking mode for GPT-5 and Gemini 2.5 Pro and probably some of the other models. But I think that's also a general. I think that's also a general question where I see potential improvements. Is basically if you have a reasoning model and you plugged it into a multi-turn problem-solving space, it is
Hmm.
very slow and costly, right? Because like
Yeah,
for those kind of visual puzzles, you don't really see human have to like think for a minute and then just only to make the next step. a lot of things just seem very intuitive to humans, and human just proceed with a specific step without a lot of thinking. But models seem to not have that intuition in order to make that step. I mean, like for single step problems like math problems or competitive programming problems, you see models think, and I think I do think that makes sense, because even for humans, they write a lot of like thinking steps, a lot of steps to kind of to break down the problem into intermediate problems and to solve it, right? But for those kind of visual puzzles that are this simple and a lot of times depends on intuition, right?
Yeah.
I think it's also important to think about like how we should improve the model so that it uses its intuition to solve the problem instead of like explicit thinking that generates a lot of like 1,000 tokens before it generates the action token, which is only like 3 or 4 tokens, right? So I think this is something that I see as an area of improvement. Basically, how the we should really distill this kind of reasoning into intuition for these models in order to solve, in order to be better solvers of multi-step tasks.
Yeah, I think it also kind of goes into like a lot of these terms. Like you have seen like every model, every frontier model has like thinking mode, and sometimes you don't really need for the specific task, but it just goes on for like thinking mode for like 1-2 minutes and came to like like this answer, and sometimes it's not really required for a simple task. Yeah, I got it. And I think that's all the questions I have. Like, thank you for answering my questions. And if anyone has any more questions, please feel free to ask. Think we are good. Yeah.
Great.
Yeah. Thank you, Colin, for a great presentation. And yeah, I hope like once you when we see the like next version of VisGym, I hope you'll come back and let us.
Someone asked, am I gonna share the slides? Yes.
Yeah.
I think the video will be shared, but I will also put this slide into the VisGym website later if you find it useful. So it will basically, yeah. Go ahead.
Yeah, I mean, if you can share it with me, I can just share it with the whole community.
Oh, okay.
Like if you are willing to share.
Yeah. So I will share the slides with you. I think the video will also be shared.
Yeah.
And at the same time, I will probably put the slide in the website of VisGym. So there's a website that we have, like basically visgym.github.io, where we have like VisGym. So we have like a website that basically shows the benchmark dataset models. We have the code here. It's already available that you can play with. And we also have our paper here on archive, so you can search the paper for all the detailed information. And we have those kind of demos and solver trajectories from here, so you can also try to play around and see how VisGym works. Yeah.
Okay, got it. Yeah. I think that works. Yeah. I'll share those things, and I'll get in touch with you like after this so that you can share with me and I can share with them.
Cool.
Yeah. And yeah. Thank you, Colin. Yeah, for the great presentation. Yeah.
All right. Thank you.
Yeah. Thank you. Thanks everyone for attending this session. See you.